Okay, the purpose of this presentation is to show you how to use the intrinsic so-called data transformation features in PRISM to make a hill plot or a scattered plot. At the end, I'll also show you how to convert the free ligand axis from a linear to a logarithmic scale in a very convenient way, so you can go between linear and logarithmic binding plots. But let's start with the hill and scattered analyses. So what I've done here is I've simulated some data. These data are lower quality than the actual experimental data that I gave you to analyze in the problem sets. But these are not atypical. And actually, if you pick up a journal, just about any journal any given week, you are likely to find some binding data with roughly this quality. I used the simulated data so that I could illustrate some points that I want you to pick up. And it would have been harder for me to do that with actual experimental data, especially the high quality data that we try to get before we publish something. In any event, these data, again, they're not awful. They are typical of the binding data that many people would publish. If we look at them quickly, so the idea here is there are two different experiments. Let's say these are two different receptors. Let's say bind a common ligand that we're titrating onto them. If you look at the data just superimposed in this way, it's not obvious that there is a big data difference between the red and the blue curves. They seem to move towards saturation in roughly the same manner and with roughly the same midpoint. Crudely, they seem to be saturating around a value of 80. If you look at these data, they start around 20, so they're spanning around 60. So midway would be 20 plus 30 would be 50, and that would suggest the KD is about 2 for both of them. If you think of that, of course, for an independent site binding, you have to go to 19 times the KD. In this case, if the KD is about 2, that would be 38 before you get to 95% saturation. Based on this sort of crude qualitative analysis, these things look to be saturating very quickly, and you might suspect there's some cooperativity. But as we move forward, you'll see that there are some complexities to analyzing data of this kind. And again, these data are of sort of reasonable quality. Before publishing it, if these were my data, depending on the goal of the binding analysis, I might try to go back and get some better data. But these are not such, these are reasonable quality data for publication. And one point of this is to show you the kind of pitfalls that lie in what seemed to be a routine analysis of a binding curve. But anyway, let's get on to the main point, which is to convert this to first make a hill plot, and then we'll make a scattered plot. So let's start with the hill plot. To make the hill plot, as the PowerPoint told you, you need to have a estimate of free ligand. In this case, we're assuming we know free ligand. The current plot is in free ligand. We also need to know the value at full saturation, because what we want to do is plot the bound over the free, our estimate of bound receptor over free receptor at each concentration. To do that, we need to know where it saturates. Now, we could do that crudely by just looking at the apparent plateau here. But that wouldn't be unreasonable, but it would be error prone, because the noise in the data can make, especially over a limited region of data acquisition, the noise can, let's say, create a misleading impression. And so given data of this kind, which again are reasonable, one way we can get an idea of the actual saturation level is to start by doing a nonlinear curve fitting. Now, when we do this, we're also going to get an estimate of cooperativity, and we'll see that that's actually quite a useful estimate. And that might lead you to ask, why bother doing a hill plot, or why bother doing a scattered plot? Well, in practice, the nonlinear curve fitting, when done well, in PRISM, as you're going to see shortly, actually does not do hill analyses or scatter analyses particularly well, but it does nonlinear curve fitting very, very well. The nonlinear curve fitting can be a good way to get an estimate of the cooperativity, but it's still important to know about the hill and scatter analyses, because many people will use them in journal articles. And also, when we publish data from my lab, if we are concerned about the cooperativity, we would actually beat on the experiment until we got good enough data to get a convincing either hill or scattered analysis. but you'll see in a moment that nonlinear curve fitting is actually very powerful. And so let's go ahead and do that. I will analyze it. We want to do a nonlinear regression of these data. Again, the reason I'm doing this at the moment before doing the Hill analysis is because I need an estimate of the fully saturated signal level. The nonlinear curve fitting will give me the most probable estimates of the baseline and the delta, and I will put them together, and that will give me the most probable estimate of the saturation level. So that's a powerful tool in and of itself. So I'll go ahead and do the nonlinear regression. I will pick this cooperative binding isotherm with free ligand from my undergraduate W4082, my undergraduate biophysics class. We'll just check the equation quickly. Y equals background plus delta times x to the n over kd to the n plus x to the n. X in this case is free ligand, so we've done this before. I've previously shown you how to set up all the other aspects of the equation, so we won't do that. I will note that I have reported one transform. I've asked the program to report one transform, which is P1 plus P2 in its lingo, which is P1 in this case is the background variable and P2 is the delta variable. So what I've asked it to do is sum these two together. So background plus delta gives me the value at full saturation. So I'm asking it to also report, to do the math itself and report its optimal estimate of the signal at full saturation. So let's go ahead and run the curve fitting. And although the data, the red and the blue curves, naively looked to be rather similar, now when the nonlinear curve fitting is done, there's a hint that these things are actually significantly different. The red curve looks rather hyperbolic. The blue curve looks rather sigmoidal. These binding curves seem to saturate rather quickly. There was a hint of maybe cooperativity. Now we're seeing one of them really does look cooperative, but the other one, based on the most probable parameter values from nonlinear curve fitting, that looks pretty hyperbolic and looks pretty independent site. So one useful thing now will be in the Hill and Scatcherd analyses to see whether they support this interpretation that the red curve is independent site and the blue curve is cooperative. So actually, before we do that, I'm actually going to extend the range. I'm going to just redo this analysis very slightly. I'm going to ask it to plot the simulated curve up to values of 20. And why am I doing this? I'm doing this to make the point that this is showing a KD value somewhere in the 3 to 5 range, ostensibly. If that's true, the full saturation should only be achieved, somewhere, let's say, way above 15 micromolar. And so when we look at the nonlinear curve fitting, we see that these curves really are continuing to go up, and that we really are still not close to the fully saturated value. But the baseline and delta parameters estimated from the nonlinear curve fitting will now give us the most probable estimate based on that binding model of the fully saturated value. So let's go up and take a look at that. So here's the value. Here are the values in the nonlinear curve fitting. Background 1923. Okay, delta 7164. Signal at saturation, which is the sum of background and delta, in one case is 90.58, in the other case 87.80. So for various reasons, I'm going to remember the higher of these. Simply put, a signal above saturation sort of is mathematically problematic if you look at the algebra, and so we'll take the higher of these because we would rather not underestimate the signal at saturation. Okay, and so now we can look at the estimates of the n. It's saying the red curve is 1, and it is plotting a hyperbolic curve, so that's at least consistent. It's saying the blue curve is 2. So it says there is significant cooperativity, twofold or more cooperativity for the blue curve, but that the red curve is independent site binding. So we're going to see whether the Hill and Scatcherd analyses support that. It's telling us now that KD is 3.3 in one case or 3.8 in the other. It's interested to look at the error estimates here, and one in particular, because it relates to the quality of the Hill analysis, would be the signal of saturation. It's saying that the standard deviation of the signal of saturation is 12.6. So it's saying the signal of saturation is 90.58 plus or minus 12.6. That's actually quite a significant variation. It says the 95% confidence limits for that are 63 to 118. That's a huge range of variation. And from the other curve, it's saying the signal of saturation would be between 78 and 97, so a narrow range of saturation. But anyway, we're going to use this 90.58 value, so let's go back to the data and put that on the screen for a moment. And I'll just draw a little, actually I can do this over here. I'll put a, it will actually at y, I can put a line at y equals 90.58. I will put a dotted line. Do that, show grid line, dotted, let's see, this seems okay, let's see, right? So this is the most probable estimate of saturation from the red curve, but remember the range it was reporting for the red curve was basically this entire region. So, you know, this does show how analysis of binding curves can be rather a tricky business. Okay, but now let's go on and do the hill plot. And in PRISM, this is exceedingly easy. We're going to go analyze. And the hill plot, as we saw, we algebraically transformed the variables when we derived the expression for the hill point. So this is considered a transformation of the data. So we go analyze, transform. Rather than the standard functions, we're going to go to the, guess what, the pharmacology and biochemistry transforms. And we're going to ask it to do a hill plot. And it now asks us for the value at Vmax or Ymax. We decided the best estimate we have at that at the moment is 90.58. The X values that we entered were not log concentration. They were concentration. And we're going to go ahead and do this. And it has transformed the data into the proper format for the hill plot. And this being PRISM, it has automatically plotted it for us. Let's look at that. Let's stretch this out so we can see it. With everything being like little black dots, this is not so easy to see. What we can do here, these are the blue data. So I have so labeled them. I will make the blue data blue. I will then go ahead and make the red data, guess what, red. And now we have something resembling a hill plot. Now let's go ahead and do a linear regression, because the hill plot, there should be a straight line, and the slope of the straight line should be the cooperativity. So let's just do a simple linear regression on these data. Bang, PRISM makes this very convenient. Done. Well, what do we see? We see the slope. We see the red line. The red data, you know, those are giving us a pretty good line, I have to say. Its slope is very clearly lower than the blue, and that suggests the cooperativity is lower. Let's go up and look at these linear regression values. See what it gives us. It is estimating from this hill analysis the slope of the red data is 0.938, so very close to 1. The nonlinear regression also told us that was close to 1. Here it's saying 1.85. The nonlinear regression said it was over 2. But basically the hill analysis is agreeing with the nonlinear regression that the red data is close to n of 1 or non-cooperative independent site binding. The blue data are close to n equals 2. So let's come back here just for one moment. If you look at the blue curve, it doesn't look like a very good line. And so the data are noisy. Part of it is coming from that. But frankly, the way that PRISM does this data transformation is sort of stupid. And if I were to do it by hand, what I would do is actually use the most probable estimate of the baseline value that came from the nonlinear curve fitting. Because, of course, the first point in the graph, or the lowest point in the graph, might have noise in it, and that is not likely to be the best estimate of the baseline. The curve fitting gives you the most probable estimate of the baseline based on your, according to your error model. And so what I would do is I would take the baseline value from the nonlinear curve fitting, and you see that I already took the fully saturated value from the nonlinear curve fitting. And if you were to do that, you would actually get a better, straighter line for the blue data. So PRISM is doing this in a slightly obtuse way, but because I think it's impractical to ask you to do those more manual analyses, especially on a test. For the moment, we're just going to live with the analysis done by PRISM, and it's not bad. We can see that this does seem to be the red data give you roughly a straight line, slope of 1, independent site, approximately, and the blue data are giving you something closer to 2, and it looks like a cooperative binding. So that does work reasonably. Okay, let's go back now and actually try the scattered analysis. So let's go back to the simulated data, and now let's go again and analyze transform. In this case, we're going to analyze the table again with a new result sheet. Great. We're going to go for another pharmacology and biochemistry transform, this time the scattered plot. It's all ready to do that. we hit it, let it run, and it has done a scattered analysis. It's done the transform of the data into the scattered format, and it has also plotted that. And we'll take a look at that. So let's stretch this out as well. And let's make the red data red and the blue data blue. And let's, of course, this should only be linear in the case of an independent site binding, but the previous analyses have said the red data looks like independent site binding. Let's take a look at that quickly. Yeah, it looks like a decent line. Let's go ahead and then do a linear regression on that. And yeah, that's, the data are a bit noisy. But that's a decent line. That does, roughly speaking, support independent site binding. If we look at the blue curve, this is a bit messier. I mean, one thing I think you would not look at the blue curve and say, yes, that's convincingly a straight line. As I look at it, because I've looked at a lot of these things, to me it does look very curved. Certainly with that kind of scattered plot, I would certainly greatly worry that this is a cooperative binding. Again, PRISM is doing this transformation in a slightly less than ideal way. If I were to do it by hand, I would get a better looking scattered plot out of the blue data. But it would not look perfect. And this does emphasize the point that twofold cooperativity can be rather difficult to detect experimentally. But anyway, I think you can see that the scattered plot certainly looks way more curved, whereas the red plot is roughly consistent with the data does look roughly linear. Now, in practice, if I really wanted to be sure about this, I would go back and get more data. It could be true that the kind of noise level I'm getting out of these data are just intrinsic to this experiment. But of course, I can repeat the experiment. That will give me more data. I can improve the signal to noise by doing multiple measurements and averaging them together or curve fitting them simultaneously. But another thing that I would do here is actually adjust the experimental design. So let's go back to the linear binding plot. If we go down here in the scattered plot, right, the key points are really the ones at low concentration. Here we're looking at the bound the bound receptor. In practice, actually, in this case, we're just looking at the signal on the vertical axis because the signal on the vertical axis is proportional to bound receptor, and that's proportional to y bar. So in this case, actually, it's just simply plotting that arbitrary signal on the y-axis. The key here is the linearity or curvature of this plot at the low ligand values. And of course, with low ligand values, you have a low amount bound. So it's the linearity of these points at low ligand concentration. So if we come back here, right, we really want to look at the linearity of the plot in here. We simply, our best estimate of KD so far is around 3. We do not have many data points below KD. If we wanted to know with greater confidence what the cooperativity story is here, we would go back and get more data and probably actually try to get more data points here in the low concentration range. So that concludes the exercise on Hill and Scatcherd analyses in PRISM. Just to touch on logarithmic binding curves, it is very simple in PRISM to convert from a linear to a logarithmic binding curve. You simply double-click the axis. I think I went through this in the lecture, and lo and behold, it says x-axis scale linear. I will go to log 10. Bang, and I have a logarithmic binding plot. And this is now actually in exactly the format I presented it in the PowerPoint presentation. Although the axis has been scaled logarithmically, it's log base 10 scaling or logarithmic scaling of this axis, it has plotted the numbers that are actually not log L free. It is plotted, it's indicating numbers in L free, 1 micromolar ligand, 10 micromolar ligand, 100 micromolar ligand. And so these are the actual free ligand values. So although it's scaled the axis logarithmically, it's giving the actual free ligand values, and therefore it's labeled LF. And we can maybe get this to look a little bit clearer by changing the range. And so rather than 0.1, really this is going effectively only from 1. And it really doesn't go beyond about 20. Again, these are the LF values, not the log. Even though it's scaled the axis logarithmically, it's using LF values. So we can go from 1 to 20. And so now these are logarithmic binding plots. Interestingly, um, the independent site plot is looking a bit like a straight line, but I think I mean you can see that it is sigmoidal, sort of slightly sigmoidal. If we go now to the longer axis here, and so let's say the minimum we go to 0.01. It's an interesting exercise to roll it up with. Here we go to 100. Okay, so now we've plotted this over a much longer range. I can extend these curves over a longer range. So rather than ending the curve at 20, I'm going to end the curve at 100 and start the curve at until 0.01. We'll see what we get and see if it does that. Yes, it does it. Okay, and so now you can see that when we fill in the expand the modeled curve to cover a broader data range, the independent site curve does look sigmoidal, as we expect it to be. The cooperative binding curve looks more sigmoidal. In this case, actually, the simulation did involve the same KD for both of them, and so the 50% saturation level is about the same point. And so this shows how easy it is to go between linear and logarithmic binding plots, shows, again, illustrates the same principles I talked about in the PowerPoint relative to what the meaning is, what the shape is, how these things work. This exercise, because our data are really in a narrow sort of range of LF values, this doesn't illustrate really the important utility of the logarithmic binding plot in putting data in disparate concentration ranges on the same graph. But anyway, I think it gives you an idea of how this works. And so let's go back to the linear axis. And actually one point now just to end on, our data, in the red curve in particular, our highest data point was about 80. When we look at the curve fit data going out much further, we see that 80 is really not particularly close to saturation, and this curve does get much, much higher and much closer to what we think is the most likely fully saturated value. So that, I think, covers the essential points of the Hill analysis, the Scatcherd analysis, and at least provides an example of transforming the linear free ligand axis into a logarithmic axis to generate a logarithmic binding curve.